embedding. And now let's deep dive more into the architecture of the transformer model. So here you can see, after the calculation of the embedding and adding with the positional embedding, we are passing this embedding to the layer normalization, which does this mathematical formula, like it calculates the mean, variance, and then to the normalization according to that. And after that, if you can see, there are several vectors which are as q, k, v vectors, and then they are multiplied by their respective uh, q, k, v matrices, and from this calculation, they are being from basically they are being multiplied to calculate the attention matrices and then projected back as the attention residual and the attention output. Then from there it goes to the MLP layer. From there you have up and down projection matrices. So there are up and down projections, and then subsequently it moves to another transformer block where the same thing KQV vectors are there, and same thing up down projections, and this gets repeated. This is the nano GPT-3 architecture, but let's say you are interested in seeing how any particular model that you are using, how their architecture looks like. So from the first session we have learned how to load the Microsoft Phi 3 model, and so this is the same code that loads the model and the tokenizer. In the last session we have seen how to actually look at the deep inside the how tokenization work, how different models does different tokenization. So it's very easy to see the architecture of any model. So you just call the print method and it shows the all of the uh, operation that this model is performing. So it's a model Phi 3 model, the position, this embedding layer, and after it has the module layer. This is a decoder based architecture, so it is a 32 multiplication of these, meaning there are 32 subsequent things. So for example, if you can see, this was one and then there was another, so same way there will be 32. And then there is the self attention layer, the output projection, the KQV projection, and then there is the MLP layer, the layer normalization. We have seen this one, and the residual dropout, then the final normalization, then rotatory embedding, and then the linear attention head. So that's how this model is being made, and you can also look at their hyperparameters and all to get more even understanding. But this is how pretty much you can see every models that you have loaded into your environment. You cannot see for GPT-5 and 4 unless they disclose it, but pretty much for all open weights model, this is how you can see them. So now what we are more interested is how this when you see, if you go to very last of this model and coming here after the layer normalization, this is, if I will be able to zoom it properly, you can see if you are able to see it, the logic softmax, how this everything words and all converts back to actual word that needs to be predicted. That's something we'll need to understand, like how like choosing a single token from distribution, the decoding works of a tokenizer. So let's call the input the let's ask this as a question, the capit of USA, the same thing that we asked, and then let's collect the input IDs. So from tokenizer, we can pass the input, return tensor as pt. Let's collect the input IDs, and let's also bring input IDs to the CUDA. And after that, so this till this point, the input has been tokenized. Now let's pass this to the model and get the output. Dot believe it is, and so what I am trying is to get the output of the model before this LM head, and I'm just breaking it. So because then and only we'll be able to see the probability distribution, and from the LM head we'll get the output as you can see. LM head output can call model.lm head. So we can pass the model output. So this is how I was able to know like till which point I want the output. So till model I want this to be executed, and from there LM head to LM head output. So let's run it. Sorry for this typo. Return, I believe this is the correct one. Yeah, perfect. So we have captured the output in two phases, till the model and after the model the final output, so softmax output. So let's get the output token IDs. So it's LM head, and from the last one let's bring the highest probability, argmax minus, so the highest one, and then we can use tokenizer to decode uh, this token ID, because it will be a number and it will make more sense. Alright, so it says the capital of USA is, so let me do is, then it should tell Washington. So you see, this is how the uh, autoregressiveness is coming. So if I would have passed the is back to the input, and then it's doing the completion. So now let's do one thing, and let's see the shape of it. 0th dot shape. So it's a tensor of size 153072. Perfect. And now I'm interested in the shape of the LM head. So it's also same, which is not surprising. So this is how I have just given you one of the ways how can you break, and basically you can get the output till model layer 31 33. How does the output looks, and from there if you do LM head and see the output. And so this is what I wanted you to know, like you can go this much deep into the models when they are doing the generation. So it's not just the black box, everything is present in front of you, and with the help of transformers and PyTorch you will be able to in the most of the cases you will be able to see how things are working. So, and then the next step is where I want you to pay attention, is how can you speed up, now that you know the architecture and all, how can you speed up the generation. So something is called caching of KV, keys and values. So that's what we are going to see. So let's write a message. Write a very long story about a lion in woods, and let's write 1,000. So this is something like I'm asking it to generate more, so that I wanted to show you how much time does it take for generation when you are doing I mean, if this KV caching is enabled and if it is not. So generated output, since we have defined the model, so let's use it. Model.generate, or 1 second, we need, let's combine here input IDs and then tokenizer. You can pass the message turn tensor dot input IDs, and then same thing, pass the input ID to CUDA. Perfect. So we have generated the, and then we can use the collab macro as, let's measure how much time on an average per loop. I will do this multiple time, and let's see the median standard time for the generation. So let's get the generated output is model dot generate input IDs, and we can pass, what we can do is let's first do when we are not, so let's use cache as false, so that we have a baseline, like how much time does it take normally if caching is not enabled. And then next we will enable it. We just have to switch the flag. I believe it's going to take some time because it's doing the about, I think, 7 or 10 runs. Then we will be able to. So it says it takes about 4 seconds median. So let's see if what happens when we set cache to true. I believe it should be faster. Yeah, so see, it's about like 1/3 of the actual speed. So this is much more faster when you enable the KV caching. And so this is something that you should see and explore more from your end. And in this session we were able to look more inside the transformer model, the model architecture, and how can you do the KV caching. Thank you very much for, let's see you in the next session.